Hello everyone, my name is Kaining Zhang, and I'm here to present our work, The Brain Knows What You Prefer, using EEG to decode AR input preferences on behalf of all my co-authors from the Empathic Computing Lab at the University of South Australia. As we know, understanding user input preferences is very crucial in immersive environments, where the hand gestures and controllers are common. This understanding enhances user experience, supports personalization, and can improve the interaction efficiency. Our motivation starts with the challenge of current methods such as the post-task questionnaires. Those methods are often confusing for participants and fail to capture how preferences change during each interaction. There is also a gap in EEG-based preference research. Most existing studies focus on passive stimuli and do not provide insight into active tasks that require user input, such as AR interaction tasks. Therefore, our research aims to fill the gap by exploring the potential of using EEG signal to decode AR input preferences across different tasks and input methods before, during, and after interaction. So, we outline the two main research questions. How effectively can EEG signal differentiate between preferred and non-preferred input methods in an AR environment? And do EEG patterns show consistency trends across different input methods when comparing preferred and non-preferred input preferences? Now, let's move on to the design method. In this study, we used the two input methods, the hand gesture input and handhold controller input, to perform 3 AR interaction tasks. In the pointing task, there was a tagline panel with 8 buttons. Participants need to use a given input method to click the target button. And in the manipulation task, there is a yellow cube and a blue socket. Participants need to use a given input method to grab the yellow cube and place it into the blue socket. In the rotation task, there was a red cube and a blue cube. Participants need to rotate the blue cube to match the red cube's angle within 15 degrees. We designed our 3 difficulty levels, low, medium, high, based on fifth law. For the pointing and manipulation task, the difficulty level was decided by adjusting the distance of interactive objects. For the rotation task, we defined the difficulty level using the angle of rotation along the axis. Our trial design including 4 phases. Participants began with a fixation period, and this is used for EEG baseline removal. And this was followed by a preparation phase where participants were informed of the upcoming input method and can prepare for the next input method during this phase. The task execution phase is up to 12 seconds, which depending on how long it took participants to complete the task. And we also calculate the completion time from the start of the task phase until participants finish the task. The last phase is completion phase. If participants finish within 12 seconds, the system will show success. Please return to the start position. And if participant cannot complete within 12 seconds, the system will show please return to the start position. This phase is 3 seconds. Next, let's move on to the user study. Our experiment followed a within-subject design. Participants performed all 3 tasks in a different order. Each task has 6 sessions and 3 difficulty levels. In each session, we have 10 trials, including 5 hand input and 5 controller trials in randomized order. After all 10 trials, participants conducted a session self-report to choose their preferred input method between the hand and controller for the task completion. We recruited 30 participants, 50 females and 50 males aged from 21 to 60. We used the Magic Clip tool to build our task system and collect user behavior data. And we used the mobile EEG headset to capture real-time brain activity during the experiment. Now, let's talk about the EEG decoding process. We used the participants' self-reported preference to establish the preference ground truth. For example, if participants choose the hand as their preferred input, then all the hand input trials in this session will be labeled as preferred input, and all the controller trials will be labeled as non-preferred input. We segment each epoch to 3 analyze windows. The first, preparation phase, the 3 seconds before the task is joined. And the second, task phase, the last second before the task is completed. And third, completion phase, the 3 seconds after the trial's conclusion. Now let's talk about our feature extraction. We used three feature extraction methods. First, we extracted 110 PSD features for each route, which can reflect our brain activity frequency from 5 bands. Second, we extracted 1,155 coherence features per trial, which used to analyze the brain connectivity from each EEG channels. And third, we also extracted 22 sample entropy features, which can reflect the brain complexity level. Our machine learning training and optimization processing including 5 steps. First, data preprocessing, which including handling missing values, encode labels, and balance data with multi. After that, we separate our data into 70% training set and 30% testing set. Then, we use the research CV with 5-fold coarse validation for the hyperparameter tuning, and we choose the best parameter for the final model testing. For the evaluation, we assess the model preference and answer our research question using the accuracy as our metrics. Now, let's move on to the results section. This figure shows the heat map for participants' preferred input crossing 3 tasks in all sessions by all participants. For the general input preferences, we find that in the pointing and rotation tasks, the controller input was preferred by the most participants, but for the manipulation task, most participants prefer to use the hand at their input method. For the preference consistency, we find that even within the same task, same difficulty level, participants' preference still can change in a very short time, which highlights the importance of the real-time preference detection. This slide shows the classification result across models, feature set, and phases. The highest accuracy, around 86% in the hand input subset, used the PSD feature during the completion phase with XG boost. And the XG boost was the best model with an average accuracy of nearly 79%, where KN performed the worst. The completion phase had the highest accuracy, averaging 79%, and PSD was the best feature set with a mean accuracy of nearly 80%. This slide shows the PSD input preferences pattern for hand and controller input. For the hand input, the preferred input has higher PSD only in delta and theta during the preparation phase. However, in all other significant bands, the non-preferred input shows the higher PSD value. But for the controller input subset, the preferred input follows the opposite pattern, except from the delta and theta in the preparation phase where PSD is lower, but the preferred input generally shows the higher PSD across all significant bands. And for the coherence pattern, the hand input subset, we find that the preferred input has the lower coherence in the most cases, except from the higher coherence in the lower frequency band in the delta and theta during the preparation. And for the controller input set, still almost opposite patterns, we find that the preferred input has the higher coherence overall, except from the lower coherence in the delta and theta in preparation phase. This slide summarizes the key findings from our study. First, EEG shows strong potential for classifying input preferences in AR interaction tasks, which achieving up to 85.8% accuracy with the XG boost for the hand input. Second, the completion phase provides the highest classification accuracy, which highlighting its importance in input preference detection. And third, PSD features performs the best across in subset, but combining multiple features can further improve the accuracy. Finally, EEG shows opposite preference patterns for hand and controller inputs. We also have some limitation in our study. First, our experiment was conducted in a fixed environment with basic AR tasks, and second, our classification only rely on EEG signals. Finally, separate the EEG and AR devices will require the additional synchronization, and Bluetooth transmission may lead to the delay and data loss. So, in the future, we will focusing on real-world validation and integrate the multimodal data to improve the classification accuracy. Our study made some contribution. First, we conducted a study on input preferences in AR tasks using real-time EEG from 30 participants, which capturing the labeled preferences, user behavior, and EEG features. And we also evaluated multiple models across the interaction phases to identify the best classification phase and EEG features. We find that EEG shows different preference patterns for hand and controller input. Thank you for watching. For more details, please check our paper and please email me with questions.